Dear students, today we are going to talk about the improper integral. You have already know regarding the definite integral and the evaluation of definite integral. So first of all, I want you have to revisit the properties of definite integral, because on many situations in improper integral, you have to remember all those 6 or 7 properties of definite integral. So it is assumed you are knowing all the properties of definite integral. Just look, what is the definition of improper integral? In mathematics, in mathematical analysis, an improper integral is the limit of a definite integral as an endpoint of the intervals of integration approaches either a specified real number, infinity, real specified real number, infinity or minus infinity, or in some instances both the endpoints may be infinity approaches limits. Okay, such an integral is often written symbolically, just like a standard definite integral. As you know, definite integral we always define as a to b fx dx. A to b fx dx is equal to fb minus fa, provided the definite integral of small fx is capital Fx, then you may define like fb minus fa. This is the definition of definite integral. Okay, so how we will look in the next PPT. This is fb minus fa. So look the next PPT. So there are two categories of improper integral. Type 1 is the infinite limit of integration. Okay, like this, 1 to infinite, 1 by x square dx. Type 2, discontinuous integrand, integrands with vertical asymptote. Just you look, minus 1 to 1. Okay, so this is 1 by x square dx. So there are two main category of improper integral. If you know this category, a to infinity, type 1, a to infinity fx dx, this is equal, this is the same as limit b tends to infinity. If you want to write it like this, just to check, under the integral a to b fx dx, both are the same thing. Okay, and if you look here in this example, 1 to infinity 1 by x square dx, if you are talking here, it is very clear this area is nothing but 1 minus 1 by t. If this is the graph of y is equal to 1 by x square, and you are taking this area, x is equal to 1, this is the ordinate, this point is t, then this area is 1 minus 1 by t. Okay, now again you can look this is the example of improper integral of the type 1. The same you may rewrite like this also, minus infinity to b fx dx, limit a to infinity, a is here, a to infinity to b fx dx, or we can write minus infinity to 0 x e power x dx. All are these are the improper integral, and you have already gone through the several integral, such type of the several integral during evaluation of definite integral. Now, this is also one property, a to infinity fx dx is equal to b to infinity, limit a to b fx dx. Here also you can note, we are summarizing only, e minus infinity to b fx dx is equal to this. It means the improper integral a to infinity fx dx and minus infinity to fx dx. First case is are called convergent, and second case are called divergent if the limit does not exist. Okay, so these are called convergent if the corresponding limit exists, and this is called divergent if the limit does not exist. Okay, so accordingly we will select the given integral is convergent or divergent. Okay, if you look, this is a very unique problem. You want to infinity 1 by x dx. So just you concentrate on both the area. This area is known as infinite area. Okay, y is equal to 1 by x. Just to check here, asymptotic. Okay, and this area is called finite area. Y is equal to 1 by x square. This area is this finite area. Okay, similarly, minus infinity to infinity fx dx, this is also a improper integral, and for the convergent, minus infinity to infinity fx dx, if both improper integral, just for solution, a to infinity fx dx minus infinity to fx dx are convergent. Okay, then only you can say this is convergent, and you can easily solve this improper integral. If you look the example for what values of p is the integral a1 to infinity 1 by x power p dx convergent, then you have to remember this thing. This is very important for all the problem. E1 to infinity 1 by x power p dx is convergent if p is greater than 1 and divergent if p is less than or equal to 1. So you have to remember for variety of the problem. This is the very important result. Okay. Similarly, all the property, if you know the property of definite integral, then yeah, similarly you can interpret many important property like this: if fx is continuous on AB, open close interval AB, and discontinuous at A, then A to B fx dx may be written as limit c tends to A plus c to b fx dx. If you look this example 0 to 1 natural logarithm of x dx or this example, then you can plot and you can do the exercise with your previous knowledge. If the direct comparison test, if you talk, let f and g be the continuous on flow open interval a to infinity with 0 is less than or equal to fx is less than or equal to gx, or every x is greater than or equal to a, then a to infinity fx dx converges if this is converges, and a to infinity gx dx diverges if this is diverges. So these are the very important result. And similarly, you can go for these problems, solution of this problem 1 to infinity sine square x by x square. This is beautiful problem. 1 to infinity 1 over under root x square minus 0 point dx. This is also a very good problem. Limit of the comparison test, how you will apply if the positive function f and g are continuous on flow open interval a to infinity, and if limit extends to infinity fx by gx equal to L and L is lying between 0 to infinity, then a to infinity fx dx and a to infinity gx dx both converges or both diverges. So we have to show 1 to infinity dx by 1 plus x square converges or investigate the convergence of 1 to infinity. These are the very beautiful example of the improper integral you go through and look. Uh, in the end, these are the only in any textbook of improper integral you will find such the integrals, and you may evaluate these integrals just for practice. Okay. Thank you very much. Thank you.